This is section 14.2 on limits and continuity. So some things are the same, some things are different than limits and continuity in Calc 1 and Calc 2. Right, so the bottom of 903, limits and continuity. And then page 904. First, here's a formal definition of limits. You don't have to worry about it, but some of you maybe didn't even have this, but epsilon delta notation, remember doing epsilon delta limits in Calc 1 perhaps. There's the corresponding multivariable sense. Notice the notation, limit as xy approaches ab, so an ordered pair approaches a particular ordered pair. Okay, and so here's the formal definition. Basically, xy is close to AB is this, except the distance is not 0. And then absolute value of f of x minus L is less than epsilon. Okay. Right, so we have that. And here's sort of an intuitive picture, figure 1, page 905, figure 1 and 2. So if we are close, xy is close to AB, but not quite at AB. So instead of in Calc 1, you move a little bit to the left or the right, you're within a certain distance, within a certain disk, okay? And then the function values are within epsilon of each other over here. It's the idea of a limit. Okay, now, one thing that's very different, figure 3 is what I have to emphasize. Now, in Calc 1, when you had the limit, you had a two-sided limit, and that's pretty much all you had. Recall you had the limit coming from the left and the limit from the right, superscripted with a minus sign or a plus sign, right? So limit as x approaches 2 is two-sided. Limit as x approaches 2 and you put a minus sign on top means you're coming only from the left. Limit as x approaches 2 and you put a plus symbol means you only come from the right. And that's all you could do. So one way you could show that a limit exists is to show that the limit from the left and the limit from the right both exist, and you got the same thing. Okay. Unfortunately, once you get into 2 dimensions or higher, there are an infinite number of ways to reach a point. So let's say I want to approach the point A comma B. You can't possibly give all the ways because here's a path that comes to A, B, here's another way, or you can squiggle around for a while and you come toward here. So you cannot prove a limit by exhausting all the possibilities because there are infinitely many possibilities, as opposed to Calc 1, all you had was coming from either the left side or the right side, right? That's all you could do. But now you can approach through a whole bunch of ways. Now, you can disprove a limit. You can disprove a limit if you can show 2 different paths that give different limits, then it's sufficient to say that the limit does not exist. Okay. You cannot prove that a limit does exist by exhibiting, let's say, 1,000 different paths which have the same limit. How do I know that the 1,001st different path gives me a different limit, right? So that would not be a way to prove that a limit exists, although, you know, by a plausibility argument, that does seem like a likely thing. Okay, so figure 4 shows an example, and this is typically how you would prove that a limit does not exist. Okay, so if you look at the red arrows, which means we're approaching from the x-axis, it looks like the function values are near 1. And if you look at the blue coming on along the y-axis, the function values are around -1. So I get 2 different limits from 2 different paths. So therefore, we can say that the limit does not exist in this particular case. All right, so that's typically how you would show that a limit does not exist in a lot of these instances. Okay. All right, for continuity, I'm not going to emphasize the definition that much on page 908. It's very similar to what we had in Calc 1. Limit as xy approaches AB, f of xy equals f of AB. Okay, so that's exactly the way it was in Calc 1, only you have an ordered pair going to a particular point, or you can have an ordered triple going to a particular point. And once again, when you have a discontinuity, sometimes the graph gets really, really strange. Okay, so you can see we got some interesting graphs here, figure 8 and figure 9 on page 909. Okay. All right, but otherwise, we're ready to start some of the problems. Again, a lot of the problems involving limits, the main idea is to show that a limit does not exist. Okay, so where are we? If I can get this thing focused, page 910. 14.2. And again, showing this for the benefit of those of you that don't have the text and aren't planning on getting it. So again, just for an instant, show you something that's semi-focused. Again, I'm not worried about the speed. You can always go back and rewind, fast forward as much as necessary. There we go. Okay. Now, just like in Calc 1, the easiest limits are the ones where it's basically just algebra 1 plug-in. Okay, so find the limit as x, y approaches 3, 2. Again, it takes a while to get used to the notation. In Calc 1, we said limit x approaches 5. Well, if this is an ordered pair, this has to be an ordered pair. Okay, if it's an ordered triple, this has to be an ordered triple. Right, so x, y approaches 3, 2. Now, if you get something simple like this, there's no problem with plugging in any real numbers. You're not dividing by 0, you're not taking the square root of a negative, you're not taking the natural log of a negative, just plug in. So x is 3, y is 2, just straight out plug it in, no big deal. So 3 squared, 2 cubed minus 4 times 2 squared, punch it in your machine, 56. Okay, so these are the really easy ones. So they don't give us that many of these because it's just algebra 1. Again, this is not really what it's saying. It's not really saying when I plug in 3 and 2, I get 56. When you plug in numbers that are really close to 3, 2, like 3.001, 1.9999, you should get something that's close to 56. Okay, so that's the only one I need to show you of that type. Let's try something that's harder, where you don't get it as straightforward. So limit x, y approaches 0, 0 of x to the 4th minus 4y squared over x squared plus 2y squared. So here you obviously can't just plug in, you get 0, 0. So the best way to do something like this is try to exhibit two different paths which approach two different limits. Sometimes you try those two and you don't get anywhere. You might have to try a different strategy. Okay, one way to do this is I notice, okay, well, what happens along x equals 0 and y equals 0? Those are the easiest. What happens along the x-axis and y-axis? So if I let x equal 0, then it looks like I get -2. If I try y equals 0, I get x squared, and that limit would be 0. Okay, so that pretty much should do it. All right, so if I go along x equals 0, that means put a 0 here and a 0 here, then the limit as xy approaches 0, 0 is -4y squared over 2y squared, which is -2. Okay, so remember x equals 0 means the y-axis. If I come along the y-axis as I approach the origin, the y values are near -2 or at -2. However, y equals 0, remember y equals 0 means the x-axis. So put a 0 there and a 0 there. You have the limit as x, y approaches 0, 0 is x to the 4th over x squared, which is the same as x squared, and that limit is 0. Okay, so if I come along y equals 0 or the x-axis, the z values are near 0, the heights are near 0. But if I come along x equals 0 or the y-axis, the z values are at -2. So therefore, the limit does not exist. DNE does not exist because I have two different paths which have two different limits. All right, number 11, a little bit tougher. They have a sine squared here. So that leads me to believe I should try doing something with sine. Okay, limit x, y approaches 0, 0 of this thing. Again, you can't just plug in. It'll be divided by 0. Okay, so I decided, okay, what happens at x equals 0? Put a 0 here and a 0 here. Then the limit is x, y approaches 0, 0 of 0 over y to the 4th. That's just 0. Okay. Now, along y equals 0 is going to be a little bit tough because if I put a 0 here and a 0 there, I'm still going to get 0. So that isn't going to give me a different path. Okay. Instead, I'm going to try the trick. I noticed that if you add these exponents, that's 4, and both of these added up to be 4. I want something that's 4th degree. So I come along y equals sine of x. That does approach the origin, right? If you remember the sine function, sinusoidal, it does pass through the origin. Okay, so put everywhere I see y, I put sine of x. So put sine x there, I get sine squared, or sine to the 4th. And then x to the 4th, sine to the 4th, x. Okay, that one I can deal with. Okay, and now I'll play the trick of dividing top and bottom by sine to the fourth of x. Limit x, y approaches 0, 0, sine to the fourth over sine to the fourth over x to the fourth plus sine to the fourth over sine to the fourth. Okay, so that gives me 1, that gives me 1. This is x over sine of x to the fourth power. Okay, so rewriting it over here. So 1 over limit x, y approaches 0, 0 of x over sine of x to the fourth plus 1. Okay, and you might recall from Calc 1, as x, y approaches 0, 0, there's no y here. So basically x approaches 0. This limit was 1. That was one of the basic identities in Calc 1. Or you could do L'Hopital's rule. Okay, so my limit is going to be 1 over 1 to the fourth is 1. So 1 over 1 plus 1, 1/2. Right, so if I come along y equals sine of x, the limit is 1/2. But I found a different path along x equals 0 where the limit is 0. So therefore the limit does not exist. Okay, so that one was a little bit tricky. Again, what's wrong with coming along y equals 0? There's nothing wrong with it. But if I put y equals 0 here, I have 0 over x to the fourth, which is also 0. So the limit along both the x and y axes is still 0, which does not prove or disprove the limit. So I had to get clever with some other trick. Okay, 13 was a little tricky. This limit actually does exist. So we had to do a little bit of a trick here. So limit x, y approaches 0, 0 of x, y over the square root of x squared plus y squared. I divided top and bottom by absolute value of x, y. So this is absolute value of x, y. And absolute value of x, y underneath the square root becomes x squared, y squared. Okay, it's a little bit tricky. Okay, now if you look at the numerator, xy over, it's either going to be xy or the negative xy. It's basically plus or minus 1. Right, if you stop and think about it, xy over absolute xy, it's either going to be 1 or it's going to be negative 1. Might change the sign. So I have plus or minus 1 on top. Okay, on the bottom, if I divide this out, I get 1 over y squared plus divide this out 1 over x squared. Okay, and now look at what happens. The top is either 1 or negative 1. Just need to focus. The bottom gets really big. Okay, x and y are approaching 0, 0. That's huge. That's huge. Add them up, it's huge. Square root of huge. So the numerator is either plus or minus 1. The denominator is huge. So therefore the limit is 0. Okay, so that was a little bit tricky. Okay, 15, limit xy approaches 0, 0 of this thing. Okay, it's pretty easy to see that if I come along x equals 0, okay, if x equals 0, the whole top is wiped out. I have 0 over y to the fourth. So limit as xy approaches 0, 0 of this thing is equal to 0. Okay. And then what I decided to do, again, since I have y squared, y to the fourth, I want to make this whole thing fourth degree, except for the cosine of y. I can do that if I let x equals y squared. So I decided to come along x equals y squared. That way I get y squared, y to the fourth. This will become something involving y to the fourth also. And I'm not worried about the cosine of y at the moment. Okay, so if I come along x equals y squared, that does approach the origin. All right, so everywhere I see x, put y squared. So y squared cosine y. Y squared is y to the fourth plus y to the fourth. Okay, so I have y to the fourth over 2y to the fourth cosine y, which is the limit as xy approaches 0, 0 of cosine y divided by 2. And now I just plug in 0 for y. Cosine of 0 is 1, so the limit is 1/2. All right, so I have one path where the limit is 0, one path where the limit is 1/2. So once again, the limit does not exist. Okay. Again, in this instance, say, what about y equals 0? If I plug in y equals 0, I get 0 over x squared, which is also 0. So I get two paths, both along the x and y axes, with a limit of 0. So that means I can't establish the limit or disprove the limit. Okay, 17, we borrow a trick that we had in Calc 1 to find the limit. This is 0 over 0 also, but you might recall I can multiply by the conjugate of the denominator. So x squared plus y squared over radical x squared plus y squared plus 1 minus 1 multiplied by radical x squared plus y squared plus 1 plus 1 in the numerator and denominator, right? Okay, that way this becomes a minus b, a plus b, which is a squared minus b squared. So if I square this, I just get x squared plus y squared plus 1 minus 1 squared is 1. Okay, the 1's drop out, and this x squared plus y squared drops out. So I just have to limit as x, y approaches 0, 0 of this thing, square root of x squared plus y squared plus 1 plus 1. And now you can just plug in 0, 0, square root of 1 plus 1. Final answer is 2. All right, and then 21, you have a function of 3 variables. X, y, z approaches 0, 0, 0. Xy plus yz squared plus xz squared over x squared plus y squared plus z to the 4th. Okay, so I decided to come along x equals 0 and y equals 0. Might as well make things as easy as possible. So pretend x and y are both 0. That's gone, that's gone, that's gone, that's gone, that's gone. So I basically have 0 over z to the 4th, which is 0. And then, again, noticing what I have here, I see the highest power was z to the 4th. I want to force all of these to be z to the 4th. I can do that if I come along x equals z squared and y equals z squared. So I'm going to approach the origin in a strange fashion along x equals z squared and y equals z squared. If both of those are satisfied, I do come in to the origin, right? So put a z squared here, 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 and here. So I get z to the 4th, z squared, plus z squared, z to the 4th, plus z squared, z to the 4th, over z squared, z to the 4th, another z squared, z to the 4th, plus z to the 4th, and that's equal to 1. All right, so I have one path approaching 0, the other approaching 1. So again, the limit does not exist in this particular case. All right, then we have some questions involving continuity. Determine a set of points 29 where the function is continuous. Okay, it's a rational expression, right? You might recall for rational expressions, the only place we have to worry about is if the denominator is equal to 0. So I set the denominator equal to 0, but then I realized that can't happen. So 1 plus e to the x minus y equals 0, e to the x minus y equals -1. You might recall the exponential function can never come out negative. That can't happen. Okay. So where's this function defined and therefore continuous? All of R2. R2 is another way of saying the xy plane in general. (33) g of xy is radical x plus radical 1 minus x squared minus y squared. Okay, so I know x is greater than or equal to 0. This thing has to be greater than or equal to 0. That means a little bit of algebra, x squared plus y squared is less than or equal to 1. That's inside the unit circle and including unit circle, but x has to be greater than or equal to 0. So I only have this portion right over here, right? So it's everything on the unit circle and the y-axis and everything inside. Okay, so that's where the function is continuous, and that's basically where this function is defined also. Okay, 35. f of x, y, z equals arc sine of this thing. Okay, you might recall you can only take the arc sine of something between -1 and 1. Okay, so x squared plus y squared plus z squared is less than or equal to 1, but greater than or equal to -1. Well, this is always true. Okay, this is automatically greater than or equal to 0. So this is the unit sphere and its interior. So I just drew myself the unit sphere, center of the origin, radius of 1, including the boundary and everything inside. Okay, so that's where the function is continuous. Okay, finally for 37, it's a little bit of a strange question. Where is this function continuous? F of x, y equals blah, blah, blah. If x comma y is not the origin, and then 1 if I am at the origin. It's a piecewise defined function where I have a definition for everything besides the origin. and then this thing right at the origin. Okay, so this thing is defined everywhere except the origin. It's a rational function. So it's definitely going to be continuous everywhere except maybe at the origin. Okay. So all I need to do is see if I can find a path where the limit is not equal to 1. And that's easy to do. If I come along x equals 0, then the limit x, y approaching 0, 0 of this expression becomes, okay, put a 0 here and a 0 here. You get 0 over y squared, which is 0. Okay, so I found a path where the limit is 0, but the function value is 1. Okay. So in other words, the limit, which I don't even know if it exists, but it isn't going to be 1, a requirement for continuity. So therefore, the limit as xy approaches 0, 0 of f of xy is not the same as f of 0, 0. Okay. So this graph is going to be continuous on R2 minus the origin, the set consisting of the origin. So if you imagine you have the entire xy plane and everything is shaded except you punch a hole right at the origin. So it's continuous here, 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 just not at the origin. The graph is not continuous, right? Right, so these are notes for section 14.2.